The night sky looks open. To a calm eye, it seems a thing without edges. Stars scattered across the dark, planets drifting among them, the soft band of a distant galaxy lying across the black. Nothing in the view announces a limit, and yet everything the eye can see, and everything the largest telescope has ever gathered, sits inside a boundary. That boundary has no surface. It is made of no material. It has no coordinate a spacecraft could fly to. No line painted across the dark. A traveler heading outward would never bump into it, never see it glow, never pass through a gate. The boundary is real, but it is not a place. It is the edge of the observable universe, and the observable universe is not the same thing as the universe. The observable universe is the region from which light and other signals have had time to arrive. Here, during the whole of cosmic history, it is a definition built from speed and time and patience, not from a wall. Beyond it, in every direction, there may simply be more of the same, more galaxies, more voids, more slow expansion. There may also be something stranger. The honest answer is that physics cannot yet say with certainty. So the question this night turns on is quiet but large. What can be inferred about regions from which no information has yet reached us? Some of the answer has been observed directly. Some has been calculated from well-tested models. Some is allowed by current observations without being singled out by them. And some remains speculation, told carefully and labeled as such, because the universe permits thoughts it has not yet confirmed. The boundary turns out to be a limit in information, not a limit in existence. That single sentence, kept close, makes the rest of the night easier to rest in. There is no countdown here, no final wall waiting in the dark, no trapped feeling. There is a careful walk to the edge of what is known, and a long look, with as much honesty as the subject allows, at what may lie beyond the reach of any telescope. A few things to set down before the walk begins. The observable universe is roughly 13.8 billion years old, measured from the hot, dense state the visible cosmos grew out of. Its present radius, under the standard cosmological model, is on the order of 46 billion light-years. Those two numbers look like a contradiction, and one of the first tasks of the night is to show why they are not. The boundary is observer-dependent, which means that a watcher in a distant galaxy has their own observable region, centered on them, just as this one is centered here. Nothing in that fact makes one location the physical center of the universe. The center is only the center of what can be seen from it. The night moves outward in thought, not in spacecraft. It begins with the oldest light anyone has ever caught, the faint afterglow that arrives from every direction at once. It follows that light back to the moment the cosmos turned transparent. It traces the difference between the age of the universe and the radius of the region visible from inside it. It separates the several horizons that cosmologists name, because they are not the same horizon, and confusing them is the source of most of the popular mistakes. It asks what the smoothness of the visible part allows cosmologists to infer about the part just out of sight. It considers whether space might be flat, curved, finite, infinite, or folded back on itself in a shape no glance could reveal. It treats inflation, the multiverse, and cosmic topology as possibilities with very different scientific weight. And it ends where it began, at a boundary that is not a wall, looking out at a region that may be vastly larger than anything the eye has ever gathered. None of it needs to be solved tonight. The questions are old, they will keep. The first thing to understand about the observable universe is that it is not a place with a rim, it is a definition. The observable universe is the region from which signals have had time to reach a particular observer, here, during the whole of cosmic history. Change the observer, and the region changes with them. A galaxy far away has its own observable universe, centered on itself, containing a slightly different slice of the same cosmos. Every observer sits at the center of their own visible region, and none of them sits at the center of the universe itself. That distinction is easy to state and easy to lose. The Earth sits at the center of the observable universe from Earth, in the same ordinary way that any town sits at the center of its own map. The map is built around the map maker, but the town is not the center of the country, and the Earth is not the center of the cosmos. The observable universe is a sphere of arrival, not a sphere of existence. It is the volume from which light has had time to arrive. Regions outside that volume have not yet been able to send information here. Some may enter the observable region in the future, while others lie beyond the cosmic event horizon and may remain permanently causally inaccessible under the standard cosmological model. The boundary of that volume is called the particle horizon. The name is technical, but the idea is plain. The particle horizon is the present distance of the farthest thing whose light has had time to get here since the universe began. It marks the limit of causal contact so far. Light from farther away is still on its way. Light from closer in has already arrived. The horizon is a frontier in time, not a fence in space. A common image is to picture the horizon as a glowing shell around the visible cosmos, the way the rim of the sea glows at sunset. The image is useful for one breath and misleading for the next. The horizon is not a shell. It has no thickness anyone could measure, no surface anyone could land on, no material anyone could scoop. A spacecraft aimed outward would never reach it, because the horizon is defined by the history of light arriving at a particular point, not by a location in space. Flying toward the horizon simply moves the observer, and the horizon moves with them, redrawn around their new position. The horizon is a relation between an observer and the history of the cosmos, not a thing sitting out there in the dark. Another way to say it, the horizon grows. As time passes, light from farther away completes its trip and arrives. The observable universe gets larger, not because space is pushing outward against a barrier, but because more of the cosmos has had time to be seen. At the present epoch, the particle horizon's co-moving radius grows by roughly 1 light-year per year. Its proper distance changes differently because cosmic expansion contributes as well. Some of what is invisible tonight will be visible, in principle, to observers far in the future. The boundary is a moving edge of knowledge, not a fixed edge of being. This is why the language of walls and edges has to be handled with care. A wall is a thing in space. The horizon is a fact about light and time. A wall stops a traveler. The horizon stops information from having arrived so far. But the absence of a wall does not make every region reachable. A traveler heading outward would never collide with the particle horizon. Whether a destination could actually be reached depends on the future expansion history and on whether it lies within the cosmic event horizon. The horizon is not physically in the way, but cosmic causality still sets limits. The horizon is also not the place where the universe ends. The universe does not appear to end at the particle horizon, any more than the ocean ends at the horizon seen from a beach. The beachgoer sees a line where the water meets the sky, and beyond that line there is, in fact, more ocean. The line is a limit of sight, not a limit of sea. The cosmic horizon is the same kind of object, drawn across a much larger view. Beyond it, there is, by every reasonable inference, more universe. How much more, and what kind, is the question the rest of the night will keep company with. So the observable universe is finite, observer-centered, and growing. The volume that has been able to send signals to one location during the age of the cosmos. The next step is to face the strangest number attached to it. The universe is 13.8 billion years old, and the radius of the region visible from inside it is on the order of 46 billion light-years. Reconciling those two numbers is the work of the next chapter, and the reconciliation is one of the quiet beauties of modern cosmology. Here is the puzzle that stops most people the first time they meet it. The universe is about 13.8 billion years old. Nothing, it would seem, can have been traveling for longer than 13.8 billion years. So the farthest thing whose light has reached us ought to be about 13.8 billion light-years away. And yet the standard cosmological model gives the present radius of the observable universe as roughly 46 billion light-years. 46 is more than 3 times 13.8. The numbers look like a contradiction, and the contradiction feels insoluble until the role of expansion is brought in. The resolution begins with a careful separation of the things that get muddled together. The age of the universe is one quantity. The light travel time of any particular photon is another. The look-back time to a source is a third. The proper distance to that source at the moment its light was emitted is a fourth. The proper distance to the same source now, at the present cosmic time, is a fifth. And the co-moving distance, the workhorse coordinate of cosmology, is a sixth. These 6 are related, but they are not the same, and the popular mistake is to treat 2 or 3 of them as interchangeable. The age of the universe is the time elapsed since the hot, dense state the visible cosmos grew out of. It is measured indirectly through several routes, and they agree at about 13.8 billion years. This number tells how long the cosmic clock has been running. It does not, by itself, tell how far away anything is. Light travel time is how long a particular photon has been on its way. A photon emitted by a distant galaxy 10 billion years ago has a light travel time of 10 billion years. The look-back time to that galaxy is also 10 billion years, because look-back time is simply how far into the past the observer is looking when they catch that light. For the cosmic microwave background, the look-back time is almost the full age of the universe, since that light has been traveling for nearly 13.8 billion years. Light travel time and look-back time are nearly synonyms, and both are bounded by the age of the universe. So far, so intuitive. The trouble begins with distance. The galaxy whose light set out 10 billion years ago was, at the moment of emission, much closer than 10 billion light-years away. The space between that galaxy and this one was smaller then. During the 10 billion years the light was traveling, the space behind it kept expanding, so the galaxy has been carried farther and farther from the point where the light was emitted. By the time the light arrives, the galaxy that sent it is much farther away than 10 billion light-years. The light has traveled for 10 billion years, but the galaxy it came from is now more than 10 billion light-years distant. Now push the thought to the limit. The cosmic microwave background was emitted when the universe was about 380,000 years old, almost 13.8 billion years ago. At that moment, the matter that would later become the gas whose glow we now detect was much closer than it is today. The light has been traveling for nearly the age of the universe, but the matter that emitted it has been carried outward by expansion for the whole of that time. Under the standard cosmological model, the present proper distance to that matter is on the order of 46 billion light-years. That is where the 46 comes from. It is not the distance the light traveled. It is the distance, now, to the matter that emitted the light, after expansion has done its work for 13.8 billion years. This is the heart of the reconciliation. The age of the universe bounds the light travel time. It does not bound the present distance to the source, because the present distance is set by both the light travel time and the cumulative expansion of the space between source and observer. Expansion has been stretching the room the light crosses, and the source has been riding that stretching away from the emission point. The two effects combine to put the present-day source well beyond the naive 13.8 billion light-year limit. It is worth pausing on what the number 46 is and is not. It is a model-dependent quantity. It is calculated by inserting the best measured cosmological parameters, the expansion rate, the matter density, the dark energy density, and the curvature into the standard equations and integrating the expansion history forward to the present cosmic time. Change the parameters, and the number changes. It is not a ruler held up to the sky. It is the output of a calculation that has been checked against a great many observations and has survived those checks. But it remains a calculated distance, not a directly measured one. It is also not eternally fixed. As the universe ages, more light arrives, and the particle horizon moves outward. The number 46 billion light-years is the present value, at the present cosmic time. In the far future, under the standard model, The particle horizon's co-moving radius approaches a finite limit on the order of 60-some billion light-years, because accelerated expansion prevents signals from ever reaching us from sufficiently distant regions. The horizon grows, but it grows toward a ceiling rather than toward infinity. So the paradox dissolves. 13.8 billion years is the age. 46 billion light-years is the present co-moving radius under the Standard Model, a distance calculated from a model that includes the effects of expansion. They are two different answers to two different questions, and the next chapter will sort out exactly which distance is being measured, when, and why cosmologists keep so many of them in play. Light, in cosmology, is a messenger with a habit of changing on the way. It leaves a source with one wavelength, travels across an expanding space, and arrives with another. Reading the message correctly means knowing what the crossing did to it. The first tool for that reading is redshift. Redshift is the stretching of a photon's wavelength as the space it travels through expands. A photon emitted in the blue becomes, after a long crossing of an expanding cosmos, a photon received in the red. The change is not caused by the source moving away through a fixed space, the way an ambulance siren drops in pitch as it drives off. It is caused by the space between source and observer growing while the photon is in transit. The wavelength stretches with the space. Cosmologists write this as a number, the redshift, often labeled Z, and it is one of the most useful quantities in the whole subject. A redshift of 1 means the wavelength has doubled. A redshift of 10 means it has grown by a factor of 11. The cosmic microwave background arrives with a redshift of about 1100, meaning the space it crossed has expanded by a factor of roughly 1100 since the light was emitted. Redshift is what makes the distant universe readable at all. A spectrum of a galaxy shows the same patterns of hydrogen and oxygen and carbon, but shifted toward the red by a precise amount. That amount is the redshift, and from it, cosmologists recover how much the universe has expanded since the light was emitted. Redshift is the cosmic clock face, red from the stretching of light itself. But redshift alone does not give a distance. It gives an expansion factor. Turning an expansion factor into a distance requires a model of how the expansion has unfolded, and that model, in turn, requires the cosmological parameters. This is why cosmologists speak of distances being model-dependent. The redshift is measured. The distance is calculated from the redshift using a model. Several distinct distances come out of that calculation, and each is the right answer to a different question. The light travel distance, also called the look-back distance, is the distance the photon would have covered if space had not been expanding, which is to say, the speed of light multiplied by the travel time. For a galaxy at redshift 1, this is a number less than the age of the universe times the speed of light. The light travel distance is intuitive, but it is not a distance anyone could measure with a ruler at any single cosmic instant. The proper distance at emission is the distance between source and observer at the moment the light was emitted, measured along a slice of constant cosmic time. It is smaller than the light travel distance, because the universe was smaller then. For the cosmic microwave background, the proper distance at emission was only on the order of 40 million light-years, even though the light has been traveling for nearly 13.8 billion years. The space was that much smaller. The proper distance at the present cosmic time is the distance between the source and the observer now, measured along the present slice of constant cosmic time. This is the number that comes out near 46 billion light-years for the matter that emitted the cosmic microwave background. It is the answer to the question, if a ruler could be laid down today, all at once, how far away is that matter now? The co-moving distance is a slightly different beast. Co-moving coordinates are chosen so that galaxies carried along by the expansion have fixed coordinates. The co-moving distance between two galaxies that are simply riding the expansion does not change with time. It is a label attached to the pair, not a distance that grows. The present proper distance equals the co-moving distance at the present cosmic time, which is why the two are often used interchangeably in popular accounts. They are not quite the same concept, but at the present moment they give the same number. There are more distances still. The angular diameter distance, which governs how large an object appears on the sky, behaves counterintuitively at high redshift, with objects beyond a redshift of about 1.5 appearing larger as they are placed farther away, because the universe was so much smaller when their light was emitted. The luminosity distance, which governs how bright an object appears, grows with redshift in yet another way. The classic reference for all of this is a short, careful paper by the astronomer David Hogg, written in 1999, called Distance Measures in Cosmology, which lists the formulas for a dozen different distances and explains when each applies. The reason all of this matters for the night's central question is that the boundary of the observable universe is described in the co-moving distance, evaluated at the present cosmic time. The number 46 billion light-years is the present co-moving radius of the region whose light has had time to arrive. It is not a place a traveler would reach, not a wall, but a coordinate, calculated from a model, that tells how far away, now, is the matter whose light is only just arriving. The matter that sent the light has been carried, by the same expansion that stretched the light, to a distance that exceeds the light travel time by a factor of more than 3. So the paradox of the last chapter has its roots here. The age of the universe bounds the light travel time. The present, co-moving distance to the source of the oldest light is a different quantity, one that has accumulated the effects of expansion for the whole of cosmic history. Holding these two apart is the first discipline of cosmology, and once they are held apart, the rest of the subject begins to come into focus. The next stop is the light itself, the oldest light anyone has ever caught, and the wall it marks. The oldest light anyone has ever caught arrives from every direction at once. It is not bright. It does not arrive as visible light at all. It comes in as microwaves, fainter than the warmth of a breath against a cold window, soaking the entire sky in a hiss that was first noticed by 2 radio engineers who were trying to get rid of it. That hiss is the cosmic microwave background, and it is the farthest back in time that ordinary light can take us. To see why, the picture has to be rolled backward. For roughly the first 380,000 years after the hot, dense state, the universe was opaque. It was filled with a glowing fog of free electrons and nuclei, so crowded and so hot that light could not travel in a straight line. Every photon, the instant it set out, scattered off a free electron and went off in another direction. The cosmos was luminous and blind at the same time. No photon could carry an image from one place to another, because it could not get through. Then the universe cooled enough for electrons and nuclei to combine into neutral atoms. The event is called recombination, though the name is slightly misleading, since the electrons and nuclei were combining for the first time. Once the free electrons were locked away inside neutral hydrogen and helium, the photons had nothing to scatter off. The fog cleared. The light that had been bouncing around was set free, and it has been traveling, almost undisturbed, ever since. That light is the cosmic microwave background. The moment of release is called the surface of last scattering, and it is worth holding the phrase carefully. The surface of last scattering is not a surface in space, sitting out at some distance like the shell of a bubble. It is a surface in time. It surrounds every observer, at the distance corresponding to the look-back time of 380,000 years after the beginning. A watcher in a distant galaxy has their own surface of last scattering, centered on them, at the same look-back time. The surface is observer-dependent, the way the particle horizon is. It marks the moment the cosmos turned transparent, not a place where transparency begins. The light from that surface has been stretched by expansion by a factor of roughly 1100. It was emitted at a temperature of about 3,000 degrees, in the visible and near-infrared, the color of a hot ember. It arrives now at a temperature of 2.7255 degrees above absolute zero, in the microwave band, the color of almost nothing at all. The stretching is the redshift, and the redshift of the cosmic microwave background is the largest redshift from which any light has been gathered. It is the look-back limit for electromagnetic radiation. This is why the cosmic microwave background is so often called the oldest light in the sky. It is the oldest electromagnetic radiation that can be observed directly. It is not the beginning of the universe. The universe had a history for 380,000 years before the photons of the background were set free, and that earlier history is not lost, only harder to read. The cosmic microwave background is a wall for light, not a wall for everything. Other messengers may carry information from earlier times. One such messenger, in principle, is the cosmic neutrino background. Neutrinos are ghostly particles that interact only through the weak force and gravity, and they decoupled from the rest of the cosmic contents when the universe was about 1 second old, far earlier than the photons of the microwave background. A cosmic neutrino background, predicted by the standard cosmological model, would carry information from that epoch, the first second after the hot, dense state. The neutrinos themselves have never been directly detected. They have been inferred through their effect on the cosmic microwave background and on the growth of large-scale structure, but the relic neutrinos themselves have not been caught. There is a proposed experiment called Ptolemy that would attempt the first direct detection by capturing the rare interactions of relic neutrinos with atomic tritium, it has not yet delivered a detection. The cosmic neutrino background is, at present, an inference strongly supported by indirect evidence, not an observation. Another messenger, in principle, is a primordial background of gravitational waves. Gravitational waves are ripples in the shape of space itself, predicted by general relativity and confirmed, in a different context, by the LIGO observatories in the 2010s. A primordial background, dating from the earliest moments of the cosmos, would pass through the opaque fog that stopped the photons, because gravitational waves interact so weakly that almost nothing absorbs them. Such a background has not been detected. Its presence is one of the things a sufficiently sensitive measurement of the polarization of the cosmic microwave background could reveal, through a faint twisting pattern called the B mode. The search has had a celebrated false start, a claim in 2014 that was traced to dust in the Milky Way, and it continues, night after night, on the high, dry mountains and at the South Pole. So far, no primordial gravitational wave background has been conclusively found. So the cosmic microwave background is the oldest light directly observed, but it is not the absolute limit of what might one day be read. It is a wall for photons, set at the moment the fog cleared. Beyond it, in the earlier 380,000 years, the universe was real and active and full of physics. The neutrino background and the gravitational wave background, if ever caught, would carry information from those earlier epochs. For now, the microwave background is the oldest portrait of the cosmos anyone has, and it is also the cleanest marker of where direct observation, by light, runs into its first wall. The next horizon to meet is not a wall in time, but a boundary in causal contact, the particle horizon, and it is the horizon that defines, in the strict sense, what is observable at all. The particle horizon is the horizon that gives the observable universe its size. It is the present distance of the farthest thing whose signal has had time to arrive here since the beginning. Everything inside it is, in principle, observable. Everything outside it is, for now, beyond causal contact. The particle horizon is the boundary of the observable region, drawn at the present cosmic time. The definition is precise, and the precision is what separates it from the more familiar horizons. The particle horizon is not the distance at which galaxies recede faster than light, which is the Hubble sphere. It is not the distance beyond which signals sent now will never reach the observer, which is the event horizon. It is, specifically, the co-moving distance that light could have traveled from the beginning of the cosmos to the present moment, given the actual expansion history. That distance, evaluated today, is on the order of 46 billion light-years. The particle horizon concerns the past. It tells what has had time to arrive. The cosmic microwave background arrives from a co-moving distance near the particle horizon because its light has been traveling for almost the full age of the universe. The faint galaxies, imaged by the great telescopes, arrive from somewhat smaller co-moving distances because their light set out later. The whole catalog of observed objects, from the nearest stars to the most distant galaxies to the microwave background itself, fills the interior of the particle horizon, the volume from which signals have arrived so far. The particle horizon grows with cosmic time. As the universe ages, light from more distant regions completes its long trip and arrives. At the present epoch, its calm-moving radius advances by roughly 1 light-year per year. This is the sense in which the observable universe gets larger. It is not that space is pushing outward against a barrier. It is that more of the cosmos has had time to be seen. An observer 1 billion years from now will have a somewhat larger observable region than the one available tonight, because light from some regions currently just outside the particle horizon will have arrived. The growth is not without limit, at least under the standard model. The same accelerated expansion that is carrying distant galaxies away faster and faster also limits how much of the cosmos will ever be observable. As the horizon moves outward, the regions it is moving toward are being carried away by expansion, and at some point, the recession outpaces the arrival of new light. Under the standard cosmological model, with dark energy behaving as a cosmological constant, the particle horizon approaches a finite asymptote. The co-moving radius of the observable universe will grow toward a limit on the order of 60-some billion light-years and will not exceed it. There is a ceiling on how much of the cosmos will ever be observable, even given infinite patience. This is a subtle point, and it is worth separating from a related one. The particle horizon is the boundary of what is observable now. The event horizon, which will come in a later chapter, is the boundary of what will ever be observable in the future, given an assumed expansion history. The two are different horizons, and they behave differently. The particle horizon grows, asymptotically, toward a finite limit. The event horizon sits at a smaller distance and shrinks in co-moving terms, as the accelerated expansion carries regions across it out of future view. Confusing them is one of the standard cosmological mistakes, and the night will keep them clearly apart. The particle horizon is also not a physical surface. It is a coordinate, calculated from the expansion history, that tells where the boundary of present observation falls. A traveler heading outward would not encounter it. Depending on the future expansion and the destination, a traveler could in principle reach some regions whose light has not yet reached the starting point, while regions beyond the cosmic event horizon would remain inaccessible under the standard model. The particle horizon is a fact about the propagation of light across cosmic history, not a fact about the geography of space. It is worth noting, too, that the particle horizon is defined with respect to a particular observer. Every observer has one. A galaxy at the edge of the observable universe from here has its own particle horizon, centered on itself. The particle horizons of widely separated observers overlap only partially, and there are regions of the cosmos observable from here, but not from a distant galaxy, and vice versa. The particle horizon also marks the boundary of causal contact so far. Two regions whose particle horizons have never overlapped have never exchanged signals. In the standard cosmological model without inflation, there would be a great many such regions in the visible universe, and the uniformity of the cosmic microwave background across the sky would be a puzzle. This is the horizon problem. and it is one of the motivations for inflation, which will come later in the night. The next chapter turns to the geometry in which all of this is happening, the expansion that carries galaxies apart and stretches the space through which the light travels, and to the question that almost every newcomer asks first: how can anything recede faster than light without breaking the rule that nothing does? The expansion of the universe is the single fact that makes everything in the last 3 chapters work. It is also the single fact that produces the most persistent misunderstanding in popular cosmology. The misunderstanding is the idea that the expansion is a kind of motion through space, and that the speed limit of relativity therefore applies to it. Both halves of that idea are wrong, and untangling them is the work of this chapter. The expansion of the universe is not motion through space. It is an increase in the distance between things, caused by the metric of space itself changing with time. The technical name is metric expansion. The metric is the mathematical object that defines distances in space, and in an expanding universe, the metric grows with cosmic time, so that the distance between any 2 sufficiently separated points increases, even though neither point is moving through space in the ordinary sense. The points are carried apart by the change in the metric, the way 2 dots drawn on the surface of an inflating balloon are carried apart by the stretching of the rubber. Even though neither dot is crawling across the rubber toward or away from the other. The things carried along by the expansion are called co-moving observers. A co-moving observer is an idealized watcher who has no peculiar motion of their own, who is simply riding the expansion. Galaxies, on the largest scales, are approximately co-moving observers. They have small, peculiar motions. The Andromeda Galaxy is approaching the Milky Way, for instance. But on the scale of the cosmos, these are small corrections. Treat the galaxies as co-moving, and the picture simplifies to a set of points carried apart by a growing metric. The rate at which the distance between 2 co-moving observers grows is proportional to the distance between them. This is Hubble's law, named for the observer whose measurements first established it, though the relationship had been derived from theory a few years earlier. A galaxy twice as far away recedes twice as fast. A galaxy 10 times as far away recedes 10 times as fast. The constant of proportionality is the Hubble parameter, and its present value is on the order of 70 kilometers per second per megaparsec, where a megaparsec is about 3.3 million light years. Now comes the point that stops most people. If the recession rate is proportional to distance, then at some distance, the recession rate reaches the speed of light. That distance is the Hubble radius, and it is on the order of 14 billion light years. Galaxies beyond the Hubble radius are receding faster than light. Their recession velocity exceeds the speed of light, and yet they are observable. The cosmic microwave background, whose source is at a co-moving distance of 46 billion light years, was emitted by matter that has been receding faster than light for almost the whole of cosmic history. Its light has arrived anyway. This is the moment to be very careful about what is and is not being said. The recession velocity is not a velocity through space. It is the rate at which the metric distance between two co-moving observers is growing. Nothing is moving through space past a nearby observer at a speed greater than light, the speed limit of special relativity, that nothing with mass can be accelerated past the speed of light through local space, is not violated, because the recession is not a local velocity through space. It is a global rate of change of distance produced by the changing metric. The analogy of the balloon helps here, with a caution attached. Two dots on an inflating balloon move apart because the rubber stretches, not because either dot crawls across the rubber. The speed at which the distance between them grows can be made arbitrarily large by choosing dots far enough apart, but no dot is moving across the rubber faster than the speed of light. The recession is in the rubber, not on it. The caution is that the balloon is a two-dimensional surface embedded in a three-dimensional room, and the universe is not, as far as anyone knows, embedded in a higher dimensional space in the same way. The analogy is a tool for the imagination, not a model of the actual geometry. A phrase often heard is that space itself can expand faster than light. The phrase is not wrong exactly, but it is misleading if left unqualified. What is true is that the rate of increase of the metric distance between two sufficiently separated co-moving observers can exceed the speed of light, and that this does not violate relativity. What is misleading is the implication that space is a substance moving through some larger arena, the way a river flows. Space is not a substance, and there is no larger arena. The expansion is a change in the metric, which is the mathematical description of distances, not a motion of a thing called space through a place called outside. It is also worth being clear about what the speed limit of relativity does say. Special relativity says that no signal, no information, no object with mass can be transmitted faster than light through local space. General relativity, which is the theory that describes the expanding universe, reduces locally to special relativity. In any small enough region, the speed limit holds exactly. The expansion is a large-scale, global effect, built up from many small regions, in each of which the speed limit is respected. There is no point in the cosmos at which a local observer measures a nearby object moving past them faster than light. The superluminal recession is a statement about the integrated distance across many local regions, each of which is perfectly well behaved. The other thing to be clear about is that expansion does not happen everywhere, on all scales. Bound systems do not expand. The Earth is not getting larger, because gravity holds it together. The solar system is not expanding, because it is gravitationally bound. The Milky Way is not expanding, because its stars are bound to each other. Even the local group of galaxies is not expanding, because its members are gravitationally bound to each other. The expansion is a large-scale effect, visible only on scales larger than the local group, where the average motion of galaxies takes over from their local gravitational relationships. The cosmic expansion carries galaxy clusters apart, but it does not stretch the clusters themselves. This is why the Andromeda Galaxy is approaching the Milky Way, even though the universe is expanding. The two galaxies are gravitationally bound to each other, and their local motion overrides the cosmic expansion. In about 4 billion years, they will merge. The expansion will continue, on larger scales, the whole time. Local physics and global expansion coexist without conflict, because they operate on different scales. The expansion is real, and it is the engine of the age and distance reconciliation, and it does not break any of the rules. The next chapter takes up the horizon that the expansion produces, the Hubble sphere, and the common mistake of treating it as the edge of the observable universe. The Hubble sphere is the horizon most often mistaken for the edge of the observable universe. It is the distance at which the recession velocity equals the speed of light. Inside the Hubble sphere, galaxies recede slower than light. Outside it, they recede faster. At the present epoch, the Hubble sphere lies roughly 14 billion light-years away, well inside the particle horizon at 46 billion, and it is not, in any sense, the boundary of what can be seen. The mistake is understandable. The reasoning goes, light from a galaxy receding faster than light can never reach us. So galaxies beyond the Hubble sphere are invisible. So the Hubble sphere is the edge of the observable universe. Each step sounds reasonable. Each step is wrong, and the wrongness is instructive. The first wrong step is the assumption that light from a superluminally receding galaxy can never reach us. It can, and it does. The cosmic microwave background is the proof. The matter that emitted the cosmic microwave background has been receding faster than light, in the metric sense, for almost the whole of cosmic history, and yet its light arrived here long ago and is arriving now, in every direction, at the low hum of 2.7255 degrees. How this is possible is the subtlety at the heart of the matter. The key is that the Hubble sphere is not fixed, it moves. The Hubble radius depends on the Hubble parameter, and the Hubble parameter changes with cosmic time. In the early universe, the Hubble parameter was much larger, and the Hubble radius was much smaller. As the universe expanded and the Hubble parameter decreased, the Hubble radius grew. A photon emitted from a galaxy that was, at the moment of emission, receding faster than light, could find itself in a region of space that was being carried outward, but that the growing Hubble sphere was about to overtake. Once the photon is inside the Hubble sphere, it is in a region where the local recession is slower than light, and it can make progress toward the observer. It arrives, eventually, even though the galaxy that emitted it was receding superluminally at the time. This is the resolution found in a careful paper by Tamara Davis and Charles Lineweaver, published in 2004, called Expanding Confusion, a title whose double meaning is deliberate. The paper works through the common misconceptions about cosmological horizons and shows, with clear diagrams, that the observable universe contains many galaxies whose recession velocities have always been greater than the speed of light. The cosmic microwave background is the most distant example. The paper also shows that the Hubble sphere, far from being the edge of observation, is a moving boundary inside the particle horizon, and that light from beyond it can and does arrive. The second wrong step is the assumption that the speed limit of relativity applies to recession velocities. It does not, for the reasons given in the last chapter. The recession velocity is a global metric rate, not a local velocity through space. A photon aimed at us from a superluminally receding galaxy is, locally, always moving at the speed of light through the space around it, and it can still make net progress toward us if the Hubble sphere expands past it. The third wrong step is the assumption that the edge of the observable universe is defined by a speed. It is not. It is defined by time. The particle horizon is the distance light has had time to travel since the beginning. The Hubble sphere is the distance at which the instantaneous recession equals the speed of light. These are different definitions, and they give different distances, and the larger of the two, the particle horizon, is the one that bounds observation. It helps to picture the relative sizes at the present epoch. The proper Hubble radius is about 14 billion light-years. The proper distance to the cosmic event horizon is about 16 billion light-years. The particle horizon's present co-moving radius is about 46 billion light-years. The Hubble sphere and event horizon are close to each other, and under the standard model, their proper distances approach the same limiting scale in the far future. The particle horizon is much farther out, and it is the one that defines the observable region. The Hubble sphere sits inside it, a moving boundary that has no special status as a limit of sight. There is a further subtlety worth mentioning. In some cosmological models, particularly those in which the proper Hubble radius shrinks rather than grows, light from beyond the current Hubble sphere may never arrive. This is the situation in a phantom energy-dominated universe, a speculative model in which dark energy grows stronger with time. In such a universe, galaxies currently inside the Hubble sphere can later lie outside it, taking their future light with them. The standard model does not have this behavior. With dark energy as a cosmological constant, the proper Hubble radius grows toward the same asymptotic scale as the proper event horizon, and light from beyond the current Hubble sphere can and does arrive. The lesson is that recession velocity is a poor guide to observability. What matters is the entire expansion history, the way the Hubble sphere moves, the way the photon threads its way through the changing metric. The Davis and Lineweaver paper puts the matter plainly. Galaxies with recession velocities greater than the speed of light can be observed. The speed limit of special relativity is not violated. The Hubble sphere is not the edge of the observable universe. So the Hubble sphere marks where the instantaneous recession equals the speed of light, and it has uses in cosmological calculation, but it does not bound observation. The horizon that bounds future observation is the cosmic event horizon, the subject of the next chapter, sitting at about 16 billion light-years just outside the Hubble sphere. The particle horizon bounds the past. The cosmic event horizon bounds the future. It is the boundary of events whose signals can ever reach the observer, given an assumed expansion history. A signal emitted now from beyond the cosmic event horizon will never be seen if that expansion history continues. Expansion carries the separation outward faster than the signal can make lasting progress toward the observer. At the present epoch, the event horizon lies at a proper distance of roughly 16 billion light-years, numerically equal to its calm moving distance today. The event horizon is closer than the particle horizon. This is the first surprise. The particle horizon, at 46 billion light-years, marks the farthest regions from which signals have arrived so far. The event horizon, at roughly 16 billion light-years today, marks the farthest present events whose signals emitted now can ever arrive. The two are different horizons, and the fact that the future horizon is closer than the past horizon takes a moment to absorb. The reason is that accelerated expansion is carrying distant regions away faster and faster. Light arriving now from near the particle horizon began its journey long ago, when the expansion was slower. Signals emitted now from beyond the event horizon are so far away that the future expansion will prevent them from ever reaching the observer. The cosmic event horizon is, in this sense, a cosmological cousin of the event horizon of a black hole. A black hole's event horizon is a causal boundary beyond which outward signals cannot escape to distant observers. The cosmic event horizon is a causal boundary beyond which signals cannot reach a particular observer in the future. Both are described within general relativity, but they arise in different spacetimes and should not be treated as physically identical. A black hole prevents signals inside its horizon from escaping outward. Cosmic expansion prevents sufficiently distant signals from arriving inward. The event horizon is model-dependent in a way the particle horizon is not. The particle horizon depends on the past expansion history, which is reasonably well measured. The event horizon depends on the future expansion history, which is necessarily an extrapolation. Under the standard model, with dark energy behaving as a cosmological constant, the event horizon's proper distance tends toward a nearly constant de Sitter scale of roughly 16 to 18 billion light-years. Its co-moving radius, by contrast, gradually shrinks toward zero. The proper Hubble radius approaches the same limiting scale. The particle horizon remains a different quantity, and its co-moving radius continues to approach its own larger finite limit. If dark energy is not a cosmological constant, the picture changes. This is where current questions in cosmology touch the night's central subject. DESI's first-year cosmology results appeared in April 2024, and its 3-year Data Release 2 analysis appeared in March 2025. The baryon acoustic oscillation measurements themselves remain well described by a flat standard model, while combinations with cosmic microwave background and supernova data show a model-dependent preference for evolving dark energy. The reported strength changes with the chosen supernova compilation, ranging from about 2.8 to 4.2 standard deviations. The result is intriguing, but it is not a discovery, and it does not yet establish that dark energy changes with time. The fitted, evolving dark energy models describe the redshift range covered by present observations. They should not be projected indefinitely into the remote future as if they were established physical laws. If dark energy evolves, the event horizon could lie at a different distance, change its behavior qualitatively, or fail to exist at all. Present data do not determine which long-term future, if any, is correct. The honest conclusion is not that weakening dark energy simply moves the horizon outward, but that an uncertain future expansion history makes the future horizon uncertain as well. It is worth being clear about what is and is not established here. The accelerated expansion is strongly supported by distant supernovae and by the combined cosmological evidence. What remains uncertain is the nature of the component or physics responsible for it, called dark energy, and whether its effective equation of state remains constant with time. A cosmological constant is the simplest explanation. The combined DESI results challenge that simplest description enough to deserve attention, but systematic effects, model assumptions, and additional data remain important. Telling the possibilities apart requires more observations and independent cross-checks. So every statement about the event horizon's distant future is conditional on a model. Under the standard cosmological constant model, its proper distance tends toward a finite scale, while its co-moving radius shrinks. Under other dark energy histories, the limiting behavior could be different, or an event horizon might not exist. This is the horizon whose long-term behavior is least certain, because it depends on the part of cosmic history that has not yet happened. There is one more consequence worth noting, and it is a quietly melancholy one. Under the standard model, galaxies near the event horizon are, at this cosmic moment, sending their last observable light. As the accelerated expansion continues, more and more galaxies will cross the event horizon, in the sense that their future light will no longer be able to arrive. The galaxies will not disappear from the sky at once. Their present light will continue to arrive, increasingly redshifted for a long time. But the events happening in them now and in the future will be lost to view. An observer far in the future will see a sky in which the distant galaxies have faded to red and beyond, their light stretched to wavelengths too long to detect, their future hidden behind a horizon that has closed over them. This is not a cause for alarm. The time scale is vast, billions of years, and the local group of galaxies, the Milky Way and Andromeda and their companions, will remain gravitationally bound and visible to each other throughout. The point is only that the event horizon is a real boundary on future observation, and that accelerated expansion is slowly narrowing its co-moving reach under the standard model. The cosmos is not closing in. It is simply becoming harder to see at the largest scales as time goes on. The boundary is a limit of light set by the future of expansion, and the future of expansion is still partly to be measured. The next chapter turns from the horizons that bound observation to the question of what may lie just beyond them, in the regions whose light has not yet arrived, but whose existence is, by every reasonable inference, continuous with the visible cosmos. The horizons defined in the last few chapters are boundaries of information, not boundaries of existence. This is the sentence to keep close for the rest of the night. The particle horizon marks the limit of what has been observed so far. The event horizon marks the limit of what will ever be observed, given an expansion history. Neither marks the limit of what is. Beyond both, there is, by every reasonable inference, more universe. The simplest inference is that the regions just beyond the particle horizon are broadly similar to the regions just inside it. This inference rests on a single observed fact: the large-scale uniformity of the visible cosmos. The cosmic microwave background, observed across the whole sky, is uniform to about 1 part in 100,000 after the dipole from the observer's own motion is subtracted. The distribution of galaxies, on large enough scales, is statistically homogeneous. The large-scale structure of the cosmos, mapped by surveys of millions of galaxies, shows the same kinds of patterns in different directions and at different distances. The visible universe, on its largest scales, is smooth. Given that smoothness, the simplest assumption is that it continues. The regions just beyond the particle horizon, whose light has not yet had time to arrive, are presumed to be made of the same kinds of matter, governed by the same physics, arranged in the same kinds of large-scale patterns. There is no sharp change at the horizon. The horizon is a frontier of observation, not a frontier of nature. To suppose that the cosmos abruptly changes character at exactly the distance light has had time to travel from this particular location would be to put this particular location at the center of the cosmos in a way that has no physical justification. This is an inference, not an observation. No telescope has imaged a galaxy immediately beyond the particle horizon, by definition, because its light has not yet arrived. The claim is that, given the uniformity of the visible cosmos, the standard expectation is that the uniformity continues. The language has to match the status. This kind of inference is the workhorse of cosmology. It is the same kind of reasoning that says the centers of stars, which no one has directly observed, are presumably made of the same plasma as the surfaces which have been observed. It is the same kind of reasoning that says the far side of the moon, before any spacecraft imaged it, was presumably made of the same rock as the near side. The reasoning is sound when the underlying uniformity is well established, and it becomes more uncertain as the distance from the observed region grows. The regions just beyond the particle horizon are the safest inference. The regions vastly beyond it, trillions of light years away, are a much weaker inference because there has been no opportunity for causal contact to enforce uniformity, and because the conditions for any given model of the early cosmos may or may not hold at that remove. There is a further subtlety. The uniformity of the visible cosmos is statistical, not exact. The cosmic microwave background has structure, the famous hot and cold spots, the seeds of galaxies. The distribution of galaxies has structure, the filaments and voids of the cosmic web. The uniformity is a statement about the average on large enough scales, not a statement that every region is identical to every other. So the inference is not that the regions beyond the horizon are identical to the regions inside. The inference is that they are drawn from the same statistical distribution, that they have the same average properties, the same kinds of structures, the same kinds of variations. A galaxy beyond the horizon is not expected to be a copy of a galaxy inside. It is expected to be another galaxy, of the same general kind, in the same general environment. It is also worth being clear about what the inference does not establish. It does not establish that the universe is infinite. It does not establish that the regions beyond the horizon are infinite in extent, or even that they are vastly larger than the observable region. It establishes only that, for some distance beyond the horizon, the cosmos is expected to continue in the same general character. How far that continuation extends, whether to infinity or to a finite boundary, is a separate question, and one that the next several chapters will take up in turn. The inference is also limited by the assumption of homogeneity, which is itself a generalization from observation. If the cosmos is not in fact homogeneous on scales larger than the observable region, then the inference fails. There are models, mostly speculative, in which the observable universe sits inside a larger region of very different character, a void or a bubble, and in which the uniformity of the visible part is a local accident rather than a global feature. These models are not ruled out by observation, but they are not favored either. They require special conditions, a particular vantage point, and they cut against the simpler assumption that the visible part is typical. The standard inference, that the cosmos continues in the same character beyond the horizon, is the one that requires the fewest additional assumptions. So, the answer to what may lie just beyond present sight is, in the standard cosmology, more of the same. More galaxies, more voids, more filaments of the cosmic web, more of the slow expansion. This is the inference, supported by the observed uniformity, hedged by the understanding that it is an inference and not an observation. The next chapter turns to the principle that underwrites this inference, the cosmological principle itself, and examines what it asserts, what evidence supports it, and where its limitations lie. The cosmological principle is the assumption, woven through almost every calculation in modern cosmology, that the universe is homogeneous and isotropic on large scales. Homogeneous means that, on average, every sufficiently large region looks like every other sufficiently large region. Isotropic means that, on average, every direction looks like every other direction. The two together imply that no location is privileged and no direction is special, which is the formal way of saying that the Earth is not at the center of the cosmos, and the cosmos has no preferred axis. The principle began as an assumption, a simplifying postulate made by Einstein and by others in the early days of relativistic cosmology, on the grounds that the universe ought to look the same everywhere, unless there were reason to think otherwise. It was a philosophical preference as much as a scientific one, a kind of extended Copernican principle that refused to put the observer in a special place. In the early 20th century, with little data about the large-scale structure of the cosmos, the principle was a working hypothesis. In the early 21st century, with a great deal of data, it has become a tested approximation. The evidence comes from several independent directions. The cosmic microwave background, mapped across the whole sky by the COBE, WMAP, and Planck satellites, is uniform to 1 part in 100,000. The large-scale distribution of galaxies, mapped by surveys like the Sloan Digital Sky Survey and, more recently, by the Dark Energy Spectroscopic Instrument, shows statistical homogeneity on scales above about 100 megaparsecs, which is roughly 300 million light-years. the counts of distant radio sources, the X-ray background, the distribution of galaxy clusters, all show the same statistical uniformity on large enough scales. The universe, looked at with a wide enough view, is smooth. The principle is statistical, not exact. On small scales, the universe is wildly inhomogeneous. The solar system is almost entirely empty space, with almost all the mass concentrated in the sun. The Milky Way is a dense band of stars in a sky that is mostly dark. The local group of galaxies is a small cluster in a region that has larger clusters and vast voids. The inhomogeneity is real, and it is the subject of a great deal of astrophysics. The cosmological principle applies only on scales large enough that the local structures average out, and the scale at which they average out is itself an observational question, settled by the galaxy surveys at around 100 megaparsecs. The principle also has known anomalies, small departures from exact statistical isotropy that have been noted in the cosmic microwave background and that resist easy explanation. There is the cold spot, a region of the microwave sky that is colder than expected by some distance. There is the hemispherical power asymmetry, a slight difference in the amplitude of fluctuations between one half of the sky and the other. There is the so-called axis of evil, an unexpected alignment of the lowest multipoles of the microwave background. None of these anomalies is large. None of them, individually, is a decisive refutation of the cosmological principle. They are curiosities, the kind of small departures that may be statistical flukes, or may be hints of something more, and the community has been appropriately cautious about over-interpreting them. The principle is also limited in a deeper sense, by the existence of the particle horizon itself. The cosmological principle, as an assertion about the whole universe, extends beyond the observable region. The observations support it only within the observable region. The extension beyond the horizon is an inference of exactly the kind described in the last chapter, supported by the observed uniformity, but not directly tested. The principle is, in this sense, a working assumption that has been tested within the observable region and extrapolated beyond it. The extrapolation is reasonable, but it is an extrapolation. There is a related point about the scale of homogeneity. The cosmological principle, in its strong form, asserts that the universe is homogeneous on all scales larger than some threshold. The weak form, sometimes called the cosmological principle of mediocrity, asserts only that the observable universe is not special, that conditions here are typical of conditions in broadly similar regions. The strong form is the one used in most cosmological calculations. The weak form is the one that the observations directly support. The gap between them, on scales vastly larger than the observable region, is the gap where speculation enters, and the night will return to it. The principle is also, in a sense, self-limiting. If the universe is homogeneous on all scales, then the cosmological principle is true everywhere, and the extrapolation beyond the horizon is justified. If the universe is homogeneous only on scales up to some finite size, larger than the observable region but not infinite, then the principle is locally true and globally false, and the extrapolation fails at that finite size. The observations cannot distinguish these two cases because they only see the local region. The principle is, in this sense, a bet that the local pattern continues, and the bet has paid off so far within the observable region, but its long-range validity is not established. What the cosmological principle provides, then, is a foundation for cosmology. It is the assumption that allows the equations of general relativity to be simplified to the form used in the Standard Model. It is well tested within the observable region, hedged by known anomalies, and extrapolated beyond the horizon on the strength of its local success. The next chapter takes up the question of the geometry that the principle, combined with the observations, allows cosmologists to infer: the curvature of space. The geometry of space, on cosmic scales, comes in three kinds. Space can be flat, in which case parallel lines stay parallel, and the angles of a triangle add up to 180 degrees. Space can be open, also called hyperbolic, in which case parallel lines diverge, and the angles of a triangle add up to less than 180 degrees. Or space can be closed, also called spherical, in which case parallel lines converge, and the angles of a triangle add up to more than 180 degrees. The three cases correspond to the three possibilities for the spatial curvature, written as a number called k, which can be 0, negative, or positive. The curvature is a local geometric property, in the sense that it describes the geometry of a slice of constant cosmic time. It is not, by itself, a statement about the topology, the global connectivity of space, which is a separate question that will come in a later chapter. The curvature tells whether space, in any small patch, is flat, like a table, saddle-shaped, like a hyperbolic sheet, or spherical, like the surface of a ball. The topology tells whether the whole of space is simply connected, like an infinite plane, or multiply connected, like a torus that wraps around on itself. The observations that bear on curvature come primarily from the cosmic microwave background, specifically from the sizes of the hot and cold spots. The spots have a characteristic physical size, set by the physics of the early universe, and they appear on the sky at an angular size that depends on the geometry of the space their light has crossed. If space is flat, the spots appear at one angular size. If space is closed, the light rays converge and the spots appear larger. If space is open, the light rays diverge and the spots appear smaller. Reading the angular size of the spots is, in effect, reading the curvature of space. The Planck satellite, in its final data release, measured these spots with great precision. The Planck Collaboration's 2018 analysis, published as the 6th paper in their results series, found that the data were consistent with a spatially flat universe when combined with other cosmological data. The relevant parameter, called the curvature density and written as omega sub k, was consistent with 0. The same analysis, using only the Planck data without the additional measurements, found a slight preference for a closed universe, a small negative value of omega sub k, but the preference was within the range that could be a statistical fluctuation, and it weakened or disappeared when other data were included. That slight preference in the Planck-only data has been the subject of some discussion. A paper by Eleonora Di Valentino, Alessandro Melchiori, and Joseph Silk, published in 2020, argued that the preference was strong enough to constitute a curvature tension. The claim has not been widely accepted as evidence that the universe is closed. It has been treated as an interesting tension, a possible statistical artifact, or a hint of new physics. A careful response came from George Efstathio and Stephen Grattan, also in 2020, in a paper called "The Evidence for a Spatially Flat Universe." They used an improved version of the Planck likelihood, the statistical machinery that connects the data to the parameters, and showed that the Planck temperature and polarization spectra were consistent with a spatially flat universe. When combined with measurements of the baryon acoustic oscillations, the standard ruler imprinted on the distribution of galaxies, the constraint tightened to a curvature density of 0.0004, plus or minus 0.0018. The universe, on this combination of data, is spatially flat to a precision of about 0.2%. The most recent data from the Dark Energy Spectroscopic Instrument and from the Atacama Cosmology Telescope have continued to find consistency with spatial flatness when the data are combined, while leaving some scatter in the individual determinations. The Atacama Cosmology Telescope, in its final data release in the spring of 2025, found its measurements well fit by the standard model, with a spatially flat geometry. The Dark Energy Spectroscopic Instrument, in its second data release, found a curvature density consistent with 0 within about 2 sigma when combined with the cosmic microwave background. The overall picture is one of consistency with flatness, with some scatter in the individual measurements and some live discussion about how to interpret the scatter. It is important to be clear about what this means and what it does not. The observations are consistent with a spatially flat universe to high precision. They do not prove that the universe is perfectly flat. A perfectly flat universe has a curvature density of exactly 0, and no measurement can establish that a continuous parameter is exactly equal to a particular value. The best the observations can do is to bound the parameter to a small range around 0, and the range has been shrinking as the data have improved. The universe could be very slightly open or very slightly closed, with a curvature so small that it has not yet been detected, and the observations would still be consistent with flatness at the precision currently available. It is also important to be clear about what flatness does not imply. Flatness does not imply infinity. This is a common inference and a wrong one. A spatially flat universe can be infinite, and the simplest flat geometry, the infinite Euclidean space, is infinite. But a spatially flat universe can also be finite if its topology is multiply connected. A flat torus, the three-dimensional analog of the surface of a video game screen, where exiting one side brings the traveler back through the opposite side, is spatially flat and finite. The curvature and the topology are separate properties, and flatness constrains the topology only in the sense that it restricts the list of possible global shapes. It does not force the shape to be infinite. So the current observational situation is this: the universe, on the combination of cosmic microwave background and baryon acoustic oscillation data is spatially flat to a precision of about 0.2%, with a slight, not decisive, Planck-only preference for a closed geometry that has been the subject of discussion. Perfect flatness is not established, and the question of whether the universe is finite or infinite is not settled by the flatness measurement alone. The next chapter takes up the question of topology, the global shape, and the strange possibility that space could be finite without having an edge. The intuitive picture of a finite thing is a thing with an edge. A coin is finite, and it has a rim. A room is finite, and it has walls. The intuition is so strong that it is difficult to imagine a finite thing without an edge. And yet mathematics, and possibly physics, allows exactly that. A space can be finite, in the sense of having a finite volume, without having a boundary, in the sense of a place where the space stops. The way this works is the subject of topology, and it is one of the more quietly strange parts of cosmology. The standard analogy is the surface of a sphere. The surface of the Earth is finite, in the sense that it has a finite area, but it has no edge. A traveler walking in a straight line on the surface never reaches a rim, never falls off, never encounters a wall. They simply arrive back where they started, having gone all the way around. The surface is finite and unbounded. This is the simplest example of a space that is finite without an edge, and it is the one almost everyone can picture. The analogy has to be handled with care. The surface of the Earth is two-dimensional, and it is embedded in a three-dimensional space. The traveler walks on the surface, and the surface curves through the three-dimensional space in a way that allows it to close on itself. The universe, in the relevant description, is three-dimensional. If the universe is finite and unbounded, it is not because three-dimensional space curves through a four-dimensional space in the same way, at least not in the standard cosmological models. The closure, if it happens, is intrinsic to the three-dimensional geometry, not the result of embedding in a higher space. The sphere analogy is a tool for the imagination, not a model of the actual geometry. It shows that finite without edge is possible. It does not show that the universe is the surface of a four-dimensional ball. There is a further distinction to make. The surface of a sphere is a closed geometry, meaning it has positive curvature. A finite, unbounded space can also be flat if it has a multiply-connected topology. This is the case that the last chapter flagged, that flatness does not imply infinity. A flat, three-dimensional space can be finite if it is wrapped around on itself in the right way. The way a video game screen is finite and flat, with exiting one side bringing the traveler back through the opposite side. The simplest example is the three-torus, also called the hypertorus. Take a cube and identify opposite faces, so that moving out through the top brings the traveler back in through the bottom, and moving out through the left brings the traveler back in through the right, and similarly for front and back. The resulting space is flat in every small patch and finite in total volume. A traveler moving along one of the identified compact directions would eventually return to the starting point after circumnavigating the cosmos. A traveler moving in a more general direction could wind through the space without ever closing the path exactly. In neither case would there be an edge or boundary. This is the general idea of a multiply-connected space. The space is built by identifying points so that locations that appear separate in a covering space represent the same physical location. The identifications create the wraparound. Certain closed paths return a traveler to the starting point, not because a wall forced a turn, but because the global connectivity makes departure and return parts of one continuous route. There are many possible topologies. Euclidean three-dimensional geometry admits 10 compact flat space forms, of which the 3 torus is the simplest, and 8 complete non-compact forms, including ordinary infinite Euclidean space. Positively curved geometry admits compact possibilities, including the simply connected 3-sphere and more exotic quotients, such as the Poincaré dodecahedral space. Negatively curved geometry admits infinitely many compact topologies, as well as the simply connected infinite hyperbolic space. The list of possibilities is rich, and the observations have to sort among them. The way the observations would sort among them is through the phenomenon of repeating images. If the universe has a compact topology, and the wraparound scale is smaller than the particle horizon, then light from a distant galaxy could reach the observer by more than one path. The observer would see the same galaxy in more than one direction in the sky, the way a traveler in a mirrored room sees the same object reflected many times. The cosmic microwave background, in particular, would show matched circles, pairs of circles on the sky, with the same pattern of hot and cold spots, because the same region of the last scattering surface would be seen in 2 different directions. The searches for matched circles have been carried out using WMAP and Planck data. No definitive circle pair has been accepted as a detection. The strongest generic searches constrain the shortest non-contractible loop passing through our location to be almost as large as the co-moving diameter of the last scattering surface. That does not mean every compact topology must have a wraparound scale larger than the particle horizon. In many manifolds, the shortest closed loop can avoid our location and be substantially smaller elsewhere, so more subtle statistical signatures would be needed to find it. This is the current status. Planck data fit the simplest simply connected, spatially flat model very well, and specific topologies that would have produced detectable matched circles through our location are strongly constrained. Recent systematic work by the Compact Collaboration has also shown that the absence of ordinary matched circles leaves a broader range of complicated Euclidean manifolds observationally allowed than was once appreciated. The honest statement is that no cosmic topology has been established. Several simple candidates are constrained, and the global shape remains open. So a finite universe without an edge remains possible, in configurations and on scales not excluded by present observations. But it is not established because no specific finite topology has been detected. The night will return, in a later chapter, to the question of how such topologies might one day be tested. Inflation is the name given to a brief phase of accelerated expansion, thought to have occurred in the earliest moments of the cosmos, in which a small region of space was stretched to an enormous size by an exponentially growing scale factor. The idea was proposed in its modern form in the early 1980s by Alan Guth and by others, and it has become a central framework of early universe cosmology. Its relevance to the night's central question is that many inflationary models imply that the total inflated region is vastly larger than the part currently observable, which would place the observable universe inside a much larger cosmos. The motivation for inflation comes from a set of puzzles in the standard hot Big Bang cosmology. The first is the horizon problem, mentioned earlier, that widely separated regions of the observable universe have apparently never been in causal contact, and yet they have the same temperature to high precision. The second is the flatness problem, that the curvature of space is observed to be very close to zero, which requires the early universe to have been tuned to an extraordinary precision unless some mechanism drove it toward flatness. The third is the monopole problem, that various high-energy physics theories predict heavy relic particles, magnetic monopoles among them, that ought to be abundant in the cosmos, and yet none have been found. Inflation addresses all three by positing a phase in which a tiny causal patch, smooth and flat by assumption, was stretched to a size larger than the observable universe, diluting any relics and carrying the curvature to a value indistinguishable from zero. The framework is supported indirectly by several broad features of the cosmos: the observed flatness, the observed uniformity, the observed near-scale invariance of the primordial fluctuations, the absence of detectable magnetic monopoles. All are consistent with what inflation would produce. The cosmic microwave background, in particular, shows the kind of acoustic peaks that inflationary models predict, and the agreement between the observed peak structure and the inflationary predictions is one of the stronger pieces of indirect support. The framework is not, however, a confirmed event with a known mechanism. The driving field, the energy scale, the precise model, all remain uncertain. Inflation is a class of models, not a single theory, and the various models make different predictions for details that the observations have not yet been able to distinguish. The most direct signature, a background of primordial gravitational waves imprinted as B-mode polarization on the cosmic microwave background, has not been conclusively detected. The search continues, and the absence of detection so far constrains the simplest inflationary models without ruling out the framework as a whole. What inflation implies for the size of the cosmos depends on the model, and here the language has to be careful. Many inflationary models imply that the total inflated region is much larger than the observable patch, often by many orders of magnitude. The reasoning is that inflation, once it begins, tends to continue in most regions while ending in isolated pockets, and that the region that ended to become the observable universe is one pocket among a vastly larger inflated region. In some models, the continuation is eternal, leading to the multiverse picture that will come in the next chapter. In other models, inflation ends everywhere, but the total inflated region is still vastly larger than the observable part. The key point for the night's question is that inflation, in most of its forms, suggests that the observable universe is a small patch of a much larger cosmos. It does not prove that the cosmos is infinite. It does not directly show what exists beyond the horizon. It provides a framework in which the observable patch sits inside a larger region, and it gives a physical mechanism, the exponential stretching, by which that larger region could have been produced. The size of the larger region, whether finite or infinite, depends on the details of the model and on the duration of inflation, neither of which is settled. Inflation also does not, by itself, resolve the question of the global topology. The topology is a separate question from the size, and inflation does not uniquely determine it. The inflated region could be simply connected or multiply connected, finite or infinite, depending on the initial conditions and the global structure of the space-time. Inflation makes the local geometry flat and the local region smooth, and it makes the observable patch a small part of a larger whole, but it does not, by itself, settle the global questions. This chapter is deliberately brief because the night is not about the beginning of the cosmos. The point that matters for the present question is that inflation, as a framework, places the observable universe inside a larger cosmos, gives a mechanism by which that larger cosmos could have arisen, and leaves open the questions of its total size, its global topology, and its possible fine structure beyond the horizon. The next chapter takes up the question that inflation raises but does not settle, whether the universe might be infinite, and what infinity would and would not mean. Infinity is a mathematical possibility, not a measured object. This is the first thing to hold about the question of whether the universe is infinite. No observation has ever measured an infinite distance. No telescope has ever seen an infinite space. The most that any observation has established is that the universe, on the scales observed, is consistent with being spatially flat, and that spatial flatness is compatible with, but does not require, an infinite extent. The infinity of the universe, if it is a fact that no finite observation could establish, because no finite observation can distinguish an infinite space from a finite space larger than the observable region. This is a logical point, and it is worth stating cleanly. Suppose the universe is finite, with a wraparound scale 1 trillion times the size of the observable region. No observation within the observable region could detect the wraparound, because the repeating images would be 1 trillion times too far away to see. The observable region would look exactly as it would if the universe were infinite. The observations would be consistent with both possibilities. The distinction between a very large, finite universe and an infinite universe is not, in principle, observable from within a small patch, and the observable region is, by definition, a small patch of whatever the whole cosmos is. So the question of whether the universe is infinite is not a question that observation has answered. It is a question that the models leave open, and different models answer differently. The simplest spatially flat model, infinite Euclidean space, is infinite. A flat, compact topology, such as the 3 torus, is finite. A positively curved 3-sphere is finite. The simply connected hyperbolic space is infinite, but negatively curved geometry also admits compact, finite topologies. The observations, which are consistent with flatness, do not distinguish the infinite flat case from finite flat cases when the observable patch is smaller than the wraparound scale. What would infinity mean if it were the case? The first and most careful answer is that it would mean the spatial extent of the universe has no finite bound. It would not, by itself, mean anything stronger. There is a popular further inference from infinity to the existence of exact copies of the Earth and of every possible arrangement of matter, and this inference is much weaker than it is often presented. The inference requires, in addition to infinity, a set of assumptions about the finiteness of physically distinct states, about the statistical distribution of matter, about the homogeneity of the cosmos on scales vastly larger than the observable region, and about the way quantum states are realized. Each of these assumptions is a substantive physical claim, and none of them is established by observation. The inference, when it is made, goes roughly as follows. If the universe is infinite, and if the number of physically distinct configurations of matter in a finite region is finite, and if the cosmos is statistically homogeneous on the largest scales, then, in an infinite space, every finite configuration that has non-zero probability must occur, and indeed must occur infinitely many times. Somewhere, the argument goes, there is a region with the same distribution of matter as the observable universe, and within that region a copy of the Earth, and within that a copy of the reader. The argument is internally consistent given its assumptions. The assumptions are not established, and the conclusion is correspondingly speculative. This episode will not dwell on the duplicate Earth speculation. It is mentioned here only to be bounded, because the night's purpose is to distinguish what is established from what is allowed and what is speculative. The duplicate Earth conclusion is speculative. It depends on assumptions that go beyond what the observations support. The honest statement is that if the universe is infinite, and if certain further assumptions hold, then configurations like this one would recur. Whether those further assumptions hold is not known. Whether the universe is infinite is not known. The speculation is conditional on a tower of conditions, none of which is established, and it should not be presented as a consequence of infinity alone. What can be said more carefully is that infinity is a possibility the models allow. It is not ruled out by the observations. It is not established by the observations. It is the simplest inference if the universe is spatially flat and simply connected, but spatial flatness is not proven, and simple connectedness is not proven. And even a flat, simply connected space is only one of several possibilities the observations permit. The question of whether the universe is infinite is, at present, an open question, and the openness is not a failure of cosmology, but a consequence of the fact that the question concerns regions beyond the reach of observation. There is one more point worth making, and it is a quiet one. An infinite universe is not a more extravagant claim than a finite one, in the sense that both are consistent with the same local observations. The choice between them, in the absence of further evidence, is a choice about which model to prefer on grounds of simplicity or elegance, or fit with the rest of physics, not a choice that the data have settled. The data have settled that the observable region is very nearly flat and very nearly homogeneous. They have not settled whether the whole of which it is a part is finite or infinite. That question, like so many in this subject, sits at the edge of what observation can reach, and it waits there patiently, the way the best questions do. This chapter is the only one in the night given to the multiverse, and it is deliberately short. The multiverse is a possibility that arises in some inflationary models, not in all of them, and not as a direct observational discovery. It deserves a careful, bounded treatment, and then the night should move on. Eternal inflation is a feature of many inflationary models, in which the inflationary expansion, once begun, does not end everywhere at once. It ends in isolated pockets, where the driving field decays into the hot, dense state that becomes a local universe, while continuing in the regions between. The pocket universes, as they are sometimes called, are regions in which inflation has ended and a hot Big Bang has begun. The space between them continues to inflate, producing more pocket universes over time, in a process that has no end. The picture, in the models that produce it, is of a vast, inflating background, dotted with pocket universes, each one a separate, hot, dense state with its own history. The first thing to be clear about is that pocket universes are not visible spheres floating in ordinary pre-existing space. The popular image of bubbles in a foam is misleading if taken literally. The inflating background is a space-time with its own geometry, and the bubbles are regions within that space-time where inflation has ended. Their mature interiors are generally causally separated by the continuing inflation between them. Some eternal inflation scenarios, nevertheless, allow early bubble collisions before that separation becomes complete, and those collisions could, in principle, leave traces within a bubble such as this one. The second thing to be clear about is that no other universe has been detected. There has been no observation that has confirmed the existence of a pocket universe other than this one. The multiverse, in the eternal inflation picture, is a theoretical prediction of certain models, not an observational result. The models that produce it are not ruled out by the observations, but neither are they uniquely supported by them. The eternal inflation picture is allowed, in the sense that the observations are consistent with it, but it is not established, in the sense that the observations do not single it out. There have been proposals for observational signatures of the multiverse. The most discussed is the possibility of bubble collisions, imprints on the cosmic microwave background left by collisions between the bubble that became the observable universe and other bubbles nearby. The first systematic search for such signatures was carried out by Stephen Feeney and his collaborators using the WMAP data and published in 2011. The search found no definitive bubble collision signatures. It placed constraints on the average number of detectable collisions, ruling out a range of parameter space, and it noted that data from the Planck satellite could test the hypothesis more thoroughly. The Planck data have been examined, and no definitive bubble collision signatures have been found. The constraints have tightened, but no detection has been made. The absence of detection is not, in itself, a refutation of eternal inflation. The bubble collision signatures, if they exist, would be rare and faint, and the absence of a detectable signature in the current data is consistent with a range of models in which the collisions are too infrequent or too faint to see. The observational situation is that the simplest eternal inflation models have not produced a detectable signature, that more elaborate models can be constructed to evade the current constraints, and that no positive evidence has been found. The multiverse remains a theoretical possibility, without observational confirmation. There is a further strand of thinking, connected to the string landscape, in which the multitude of possible vacuum states in string theory is invoked to give physical content to the multiverse. The idea is that the different pocket universes could realize different vacua, with different local physics, and that the observed values of the physical constants in this universe could be the result of a selection effect, the anthropic argument, in which only universes with constants compatible with observers are observed. This is a live area of theoretical research, and it is also a source of considerable philosophical dispute. The anthropic argument is reasoning within a class of models, not a proof, and the testability of the whole framework is a subject of ongoing debate. The honest summary is this: eternal inflation and the multiverse emerge from some inflationary models, not from all of them, and not from direct observation. The pocket universes, if they exist, are regions of a larger inflating spacetime rather than visible spheres in ordinary space. Their mature interiors are generally causally separated, although some scenarios permit early collisions that could leave traces. No other universe has been detected. Proposed signatures, particularly bubble collision patterns in the cosmic microwave background, have been searched for and not found. The multiverse remains a speculative possibility, recorded carefully and then set aside. The next chapter returns to the firmer ground of what can actually be tested. The question that runs through the whole night is whether anything beyond the horizon can be known. The honest answer, repeated in different forms through the chapters, is that direct observation stops at the horizon, but indirect inference can reach further. This chapter gathers the realistic observational approaches, the methods by which cosmology tests what lies beyond the limit of direct sight. The first approach is through improved measurement of the cosmic microwave background. The temperature and polarization of the microwave sky carry an enormous amount of information about the conditions at the surface of last scattering and, through cosmological models, about earlier conditions. The Planck satellite set the full sky standard, and the Atacama Cosmology Telescope's data release 6 power spectra, released in March 2025, reached polarization white noise levels about 3 times lower than Planck across the ACT survey region. Current and planned programs, including the Simons Observatory, continuing South Pole observations such as BICEP and Keck, and the South Pole Telescope, and the JAXA-led Lightbird mission, will push polarization measurements further. Their targets include primordial B modes and finer E mode structure. None sees beyond the horizon directly. They test models of the early universe through increasingly precise observations inside it. The second approach is through searches for cosmic topology. Matched circle analyses look for repeating microwave background patterns produced when the same region of the last scattering surface is visible along more than one path. WEMMAP and Planck searches have found no accepted detection. They strongly constrain simple topologies and closed loops that pass through or near our location. But they do not force every possible compact universe to be larger than the particle horizon. In many manifolds, the shortest loop can lie elsewhere, and detecting it may require searches for off-diagonal correlations or other subtle statistical patterns rather than ordinary back-to-back circles. The low multipole anomalies have also been examined as possible topology signatures, but none has been confirmed as such. The third approach is through baryon acoustic oscillations. These are the imprint on the distribution of galaxies of the sound waves that traveled through the early universe before recombination. They provide a standard ruler, a known physical scale, that can be measured at different redshifts to map the expansion history. The Dark Energy Spectroscopic Instrument has used this ruler in its data releases to measure the expansion with new precision, and the measurements feed back into the cosmological model, constraining the curvature, the matter density, the dark energy density. The constraints on the curvature, in particular, bear on the question of whether the universe is finite or infinite, since a closed curvature would imply a finite universe. The baryon acoustic oscillation data, combined with the cosmic microwave background, give the strong constraint on flatness, and continued measurement will tighten it further. The fourth approach is through supernova distance measurements. The Type 1a supernovae, used as standard candles, provided the original evidence for the accelerated expansion in 1998, and they continue to be a primary probe of the expansion history at relatively low redshift. The Pantheon Plus compilation and the successor surveys gather large samples of supernovae and measure the distance redshift relation with improving precision. The measurements constrain the dark energy density and its equation of state, and through those, the future of the expansion, which sets the cosmic event horizon. The supernova data are one of the inputs to the current hints of evolving dark energy, and continued gathering will help resolve whether the hints harden into a discovery or fade into a statistical fluctuation. The fifth approach is through large-scale galaxy surveys. Beyond the baryon acoustic oscillation signal, the full distribution of galaxies carries information about the growth of structure, which depends on the cosmological parameters. Surveys like the Sloan Digital Sky Survey, the Dark Energy Survey, and the Dark Energy Spectroscopic Instrument map millions of galaxies and use the statistical properties of their distribution to constrain the model. The surveys also test the cosmological principle by checking the homogeneity and isotropy on the largest scales accessible. Anomalies in the large-scale distribution, if found and confirmed, could point to physics beyond the standard model, including physics relevant to the larger cosmos. The sixth approach is through gravitational lensing, the bending of light by matter, predicted by general relativity and measured with great precision, allows the distribution of matter to be mapped, including the dark matter that does not emit light. Weak lensing, the slight statistical distortion of distant galaxy shapes by intervening matter, provides a way to weigh the matter distribution on large scales. The cosmic microwave background itself is lensed by the matter between the last scattering surface and the observer, and the lensing signal in the microwave background is one of the constraints on the matter distribution and the cosmological parameters. Lensing measurements feed into the same model constraints as the other methods, and they provide an independent cross-check. The seventh approach is through constraints on primordial gravitational waves. The B-mode polarization of the cosmic microwave background, if detected at the level predicted by the simplest inflationary models, would be evidence for a background of primordial gravitational waves, and in turn for inflation at a particular energy scale. The non-detection so far constrains the energy scale and the simplest models. A detection would not see beyond the horizon, but it would test the inflationary framework that predicts a larger cosmos. The eighth approach is through future measurements of the cosmic expansion. The Hubble tension, the discrepancy between the expansion rate measured from the local distance ladder and the rate inferred from the cosmic microwave background through the model, is one of the live questions in cosmology. Resolving it would refine the model, and with it the inferences about the horizon, the curvature, and the future. The Dark Energy Spectroscopic Instrument and the James Webb Space Telescope are among the current efforts working on the tension. The ninth approach is through tests of isotropy and homogeneity. The cosmological principle is an assumption tested within the observable region, and continued testing can either strengthen it or reveal departures. A confirmed departure, on the largest scales, would be evidence that the observable region is not typical, which would bear on the inferences about the regions beyond. The 10th approach is through possible indirect signatures of pre-recombination physics. The cosmic neutrino background, if directly detected by an experiment like Ptolemy, would carry information from the first second of the cosmos, before the photons of the microwave background were set free. A primordial gravitational wave background, if detected, would carry information from earlier still. These messengers are not, strictly, beyond the particle horizon, but they carry information from epochs that the photons cannot reach, and they extend the observable past closer to the beginning. The common thread through all these approaches is that none of them sees beyond the horizon directly. An ordinary telescope cannot be made powerful enough to photograph a region whose light has not had time to arrive, because the issue is causal contact, not resolving power. What the approaches do, instead, is test the model, and through the model, infer what lies beyond. The inference is only as good as the model, and the model is tested by its predictions within the observable region. The night has walked from the boundary of the observable universe to the edge of what physics can infer about the regions beyond. It is time to gather the conclusions and sort them by their scientific weight, the way the opening promised. The sorting uses 4 categories: observed, inferred, allowed, and speculative. And the categories are not always sharp, but they are honest, and they keep the night from overclaiming. The strongest foundation is the set of observations themselves. Instruments measure the spectrum and anisotropies of the cosmic microwave background, the redshifts and angular positions of galaxies and quasars, the brightnesses of distant supernovae, baryon acoustic scales, and gravitational lensing distortions. These measurements show an expanding cosmos with an extraordinarily uniform microwave background and a statistically homogeneous large-scale galaxy distribution. They are the empirical bedrock from which cosmological parameters are inferred. The next tier is the inferred. Fitting well-tested relativistic cosmological models to those observations gives an age of approximately 13.8 billion years, a present co-moving particle horizon radius near 46 billion light-years, accelerated expansion, spatial curvature consistent with zero, and the calculated locations and behavior of the particle, Hubble, and event horizons. The same framework strongly implies a cosmic neutrino background through its effects on the microwave sky and structure growth, even though the relic neutrinos themselves have not been directly caught. The conclusion that the observable boundary is informational rather than material, and that superluminal cosmological recession does not violate local relativity, also belongs to this model-supported tier. The next tier is the allowed. The entire universe may be infinite, or finite through a compact topology, or very slightly curved beyond present sensitivity. Regions just beyond the particle horizon are expected, by the simplest extrapolation of observed homogeneity, to resemble regions just inside it, but they have not been observed. Specific global topologies remain possible, where present circle searches have limited sensitivity. A primordial gravitational wave background is predicted by many inflationary models, but no such background has been detected, and its amplitude is model-dependent. These are possibilities compatible with current evidence without being uniquely selected by it. The final tier is the speculative, eternal inflation and the multiverse, in which the observable universe is one pocket among many in a larger inflating background, emerge from some inflationary models and not from others, and they have no direct observational confirmation. The bubble collision signatures have been searched for and not found. Specific compact topologies, like the Poincaré dodecahedral space or the 3 torus, are speculative as descriptions of the actual universe, because no matched circles have been detected. Inflation itself, as a framework, is strongly motivated and supported by several broad features of the cosmos, but its precise mechanism, energy scale, and model are not confirmed, and it does not directly show what exists beyond the horizon. Duplicate Earth speculations, conditional on infinity and a tower of further assumptions, are speculative and have been set aside. These are thoughts the universe permits, told carefully and labeled, not conclusions the observations compel. The honest summary is that physics can say a great deal about the regions beyond the horizon, but what it can say is mostly of the second and third tiers, the inferred and the allowed, and very little of it is of the first tier, the observed. The boundary of the observable universe is real, and it is a boundary of information. The standard cosmological model, tested within the observable region, allows inferences about the regions beyond, and the inferences are reasonable, but they are inferences, and they are only as good as the model. The model has been remarkably successful, and it deserves the confidence it has earned, but it is not settled in all its details, and the details matter for the inferences about the larger cosmos. The current live questions, including the Hubble tension, the model-dependent Desi preference for evolving dark energy, the Planck-only curvature tension, the low multipole anomalies in the microwave background, and the non-detection of primordial gravitational waves, all bear on the inferences about the larger cosmos. None has been resolved. The DESI result is particularly important to describe precisely. The preference emerges from combinations of datasets, changes with the supernova compilation, and has not established a physical law that can safely be extrapolated into the remote future. The night began at a boundary with no surface. It returns there now, with the boundary better understood, and no more a wall than it was at the start. The observable universe is the region from which light has had time to arrive. Here, during the whole of cosmic history, it is a sphere of arrival, centered on whoever is doing the observing, redrawn around every watcher, growing slowly with time. It is not a sphere embedded in an independently observed outside, and it is not a thing with a rim. The boundary is a limit in information, not a limit in existence. The numbers have been sorted. The universe is roughly 13.8 billion years old. The present co-moving radius of the observable region is on the order of 46 billion light-years, under the Standard Model, calculated from the expansion history. The two numbers are not in conflict, because the second is a present distance that has accumulated the effects of expansion, while the first bounds only the light travel time. The cosmic microwave background is the oldest light directly observed, arriving from a surface of last scattering at a redshift of about 1100. The particle horizon bounds the past. The event horizon bounds the future. The Hubble sphere sits inside both, a moving boundary that is not the edge of anything observable. The horizons have been kept distinct because confusing them is the source of most of the popular mistakes. The particle horizon concerns signals that have arrived. The event horizon concerns signals that will ever arrive. The Hubble sphere concerns the distance at which the instantaneous recession equals the speed of light. The surface of last scattering concerns the moment the cosmos turned transparent to photons. Each is a different boundary, with a different definition, and the night has tried to keep them separate. What lies beyond the horizon, in the standard cosmology, is more of the same. More galaxies, more voids, more slow expansion, more of the calm, large-scale uniformity the visible part already shows. This is the simplest inference, supported by the observed smoothness, and it is reasonable, and it is not directly observed. The cosmological principle, the assumption of homogeneity and isotropy on large scales, underwrites the inference, and the principle is well tested within the observable region and extrapolated beyond it. How far the extrapolation holds, whether to infinity or to a finite boundary, is not settled. The universe is spatially flat to high precision, but perfect flatness is not proven, and flatness does not prove infinity. A finite universe without an edge is allowed through a compact topology, but no specific topology has been detected. Inflation places the observable patch inside a larger cosmos in most of its forms, but it does not settle the size or the shape of the larger whole. Eternal inflation and the multiverse are speculative. supported by some models and not by observation. The work of cosmology, the night has tried to show, is to make the most honest inferences possible within the boundary, and to label the point at which the inferences give way to speculation. The boundary is not a failure. It is a consequence of the finite age of the cosmos and the finite speed of light, and it would be there in any universe with those two properties. The methods of cosmology, the improved measurements of the microwave background, the searches for matched circles, the baryon acoustic oscillations, the supernova distances, the galaxy surveys, the gravitational lensing, the searches for primordial gravitational waves, all push the indirect inference as far as it can honestly go, and none of them can see beyond the horizon directly, because the issue is causal contact and not resolving power. So the night ends where it began, at a boundary that is not a wall. The universe almost certainly continues beyond the present horizon, and many well-motivated models make its total extent vastly larger than the observable region, but its full size remains unknown. The boundary separates what has been observed from what is inferred, allowed, and speculated. The particle horizon continues to move outward in cone-moving reach, gradually approaching the limit set by the future expansion history. The cosmos does not end at the limit of sight. It continues beyond the available information, while the horizon remains what it has always been, a quiet limit of knowledge and not a material edge of being.